Hello and welcome to this session in calorimetry of phase change. So, in this session, you will be learning how exactly the phase change questions can be done very easily if you focus upon the very important points. So, let's go into the learning outcome of this lesson. In this lesson, you will get to know how exactly the general method that is being used by a lot of people can only get you towards something that is confusing and you might not be able to solve the questions. But if you focus upon the reference point method that I would be telling you in a little while, I hope that would make things easier for you. So let's go and learn about this. Hello, my name is Udit Gupta and I am here because I love to teach physics. I want to make sure that all the students who come to me, they understand the topic so easily, so lucidly that they can not only do the questions on their own, but they can explain another individual as well. So, let's go on to and see when exactly can we use this reference point method. Let us say that you are given that there is a case where there is a change of phase. How exactly is it happening? Let's say we want to mix two things together, right? What are these two things? We are mixing ice and we are mixing steam. If we do mix these things, what can possibly happen? Let's find out. Here, I would like to tell the principle of calorimetry to you as well because this just might be something that is very important. Okay, what does it say? It says that the heat lost by any body must be equal to heat gained by the other body. Now obviously the loss of heat must take place from the hot body and similarly it must go and enter into the cool body which is gaining the heat over here. So you can see I've written it down for you that heat lost by the hot body must be equal to the heat gained by the cold body. I hope that this particular principle is something everybody would be knowing. It works upon the basic energy conservation laws. But can you use this to your advantage once you face a question like this? Okay, so now what do we have in the question given to us? We are given some two things if you would notice very carefully. What are these two things that is given? You are given that some amount of steam at some particular temperature is being added to some another amount of ice at some another temperature. So two things are present over here. You have steam that is at 130 degrees Celsius. Similarly, you have ice that is present at minus 15 degrees Celsius. You want to mix these two things and you want to get to know some particular questions. Now, if you see this question or this problem very comprehensively, you are going to find that there are two parts to this question. The first part of this question asks you what would be the final state of this mixture. Similarly, if you talk about the second case, it's asking about what is the final temperature. So to answer these two questions, the general method that students generally adopt seem to fail a lot. I'll tell you why. Let's say that we were given all the data that we required, that is the specific heat capacity of ice as well as water as well as steam, and let us say the latent heat for ice and steam is also given to us. So now if you go with the general method, you are going to say that let's use this principle of calorimetry, right? What should happen? Heat lost by the steam must be equal to the heat gained by ice, right? Very easy to say. But what are the possible scenarios that you can come through? Let us say if we talk about this first question, that what will be the final state of the mixture? What can you say for this question? You can say that if it so happens that there is a lot of steam but you don't have that amount of ice, it might be there that all the ice gets melted to water. Then the water reaches its boiling point and maybe it converts to steam such that at the end of the day you have all steam. Maybe it could happen that some steam is there. The steam was not this much to get all the ice converted to steam, but maybe it might happen that you have some water and some steam at 100 degrees Celsius. Another possibility could be that both of them sort of are in equivalent proportions and they just get to the point where everything becomes water. This is also one of the scenarios we cannot ignore. Wait, there are two more scenarios that can go. So even if you see that right now it's confusing, it's going to confuse you a little more, because the next cases say that if the ice is more, it might be there that you get water and ice both at 0 degrees Celsius. And if we have a lot of ice, if we don't have that much amount of heat in the steam present to us, it might be the case that it is all ice. So which case are you going to go with? How can you tell? This general method generally tells you about a very confusing tale amongst students, and that is why I want to present you the reference point method, which is a one-shot method. If you do understand the steps that are present in this question, I'm pretty sure that you would be able to crack any problem that comes in these questions, that when you talk about the phase changes happening. Okay, so what is it? Let's talk about the reference point method. What does it say? It says that whenever you have these questions that involve water, calorimetry generally would be involving the questions based on ice, water and steam. So the worst case scenario is when ice and steam are actually getting together. So I've taken up that scenario only so that this question can help you understand the reference point method and its use as well as its accuracy. So the step 1 says to us that you draw the heat curve for water. I hope everybody is probably knowing about this sort of a curve that is present if you talk about ice and steam, right? If you talk about water, over here you have ice, this is ice and water, this is water and steam, and this is steam alone, right? So if you know about this curve, which I'm pretty sure almost all of you would be knowing, you can start up from here. What is the next point that you can take? The next point is that you need to select a reference point. Where exactly should this reference point be taken? This should be taken between the points of content of mixture. So that depends where exactly your contents were. Now I will come on to the explanation part of this process as well. So we'll take that up step by step in a little while. Let's read out the other two steps as well. So this tells us step 3 that you have to mark all the heat given and heat taken. This is where the principle of calorimetry strikes in. You can say that once you talk about a hot body and a cold body, the hot body would be losing its heat. The cold body would similarly be gaining the heat. So you can say that, okay, let's mark down, let's get both of them to this reference point. Let us say there was a body that was cool, it gains temperature, reaches to a certain reference point. There was a hot body that loses temperature and comes to the certain reference point, which we can decide, which is between the contents of the mixture. And let's now just do the calculations, right? Give or take the heat now accordingly to get the final result. The fourth point that I write over here is purely logical in nature, and let's hope that you can understand this logic very easily. Okay. The good thing about this question is that you will get both the answers, both the questions that were asked to you in one go. Only these 4 steps and you're good to go. So let's check out how exactly is it done. Step number 1. What exactly had we to do? This was the most easy step. There's something that you can remember, that you have to draw the heat curve for water. If you draw this heat curve for water, I hope everybody can see that you just need to draw the curve something like this, right? You know everywhere that this solid is basically ice, this liquid is basically water, and similarly this gas is basically steam, right? Now, what was the step 2 for us? The step 2 said to us that we need to select a certain reference point. Where exactly should be this reference point? It should be between the points where the mixture, the contents of the mixture are present. So first of all, I'll see where exactly are the contents of this mixture. I can see that ice was present at some minus 15 degrees Celsius. I'll let this call as the A point. Similarly, if you talk about the other point, I can say that let us say this point is point E, where steam is present at 130 degrees Celsius. Now, where exactly should I choose the reference point? It can be anywhere. Believe me, it can be anywhere. I've just taken, for example, that let's consider that our point, reference point, is present somewhere over here. This is our reference point, that is B. And if you would be so kind to see, you can see that this is 0 degrees Celsius water point. Right? This is 0 degrees Celsius all water point. If I had to consider this point would be 0 degrees Celsius all ice point. Right? If I can consider this reference point, I would say this would be 100 degrees Celsius all water. And similarly, if I consider this as the reference point, I can say this is 100 degrees Celsius all steam. Right? So that depends how exactly you want to choose the reference point. Let us say for now our reference point is somewhere over here, that is on B. I hope that these two steps are pretty easy to understand and you might have understood both of them. So let's go to the third step. And what does this third step have for us? It says that you need to mark all the heat given and all the heat taken. How would this heat given and heat taken be seen as far as our question is concerned? You can say you want this ice to reach over here, right? Over here we would be giving the heat to the ice itself and making it reach the reference point. Similarly, if you talk about the gaseous point, that is the steam point, 130 degrees Celsius, I hope you remember the question. You need to take the heat. First, you'll get the heat down. You'll make it reach to 100 degrees Celsius steam. Then you'll have the latent heat portion. That would be the portion wherein from 100 degrees Celsius steam, we reach to 100 degrees Celsius water. And from here, we can have again the different phase change where we can say that the heat is again being lost by steam, and not really steam. Over here, if we had water at 100 degrees Celsius, the heat loses itself and we get the steam to this point as well, which is all water at 0 degrees Celsius. Now, I hope you can see there are 5 arrows in this, where 2 are for ice and 3 are for steam. So, what can we do now? Now comes the calculation point where I have written down how much heat would be taken, how much heat would be given. If let's talk about ice first, right? Let us talk about ice first, that is this point A. We are reaching from A to B. That is, we are going to give in some heat to ice so that it reaches to water at 0 degrees Celsius. How much heat should we give? So you can say that, let us say Q1 was the heat that was required to bring ice from minus 15 degrees Celsius to 0 degrees Celsius. This would be ms delta theta, that is 1500 calories. Similarly, if you talk about Q2, you can say this can be given as m into L, that is mass into the latent heat. So this would be 200 into 80, that would be 16,000 calories. Let's talk about the other case, that is steam coming down from 130 degrees Celsius to water at 0 degrees Celsius. What will you say? You will say that first of all we need this heat, that is ms delta theta. As far as steam from 130 degrees Celsius to 100 degrees Celsius is considered, the delta theta is 30, Mass was given to us 10. The specific heat is 0.5. It comes out to be 150 calories. Similarly, once we've reached here, we want this heat Q4. That is the latent heat, that we have to take from the steam from 100 degrees Celsius to convert it into water at 100 degrees Celsius. This would be some M into L. Once again, the latent heat of vaporization for steam is 540 calories per gram. So you can say that this turns out to be 5400 calories. We still haven't reached the reference point yet. It might be a little lengthy, but yes, this is almost the final step, after which we're going to use the logic. So once we want to reach from this point, that is 100 degrees Celsius water, to the point of reference, that is water at 0 degrees Celsius, you again use ms delta theta and you get this as 500 calories. Now, you have ice on one hand where two types of heat are there. I hope you can see Q1 and Q2. And you have steam on the other hand, which has three sorts of heat given as Q3, Q4 and Q5. So you can add both of them individually and then we shall use the logic. Now, what are we saying over here? What is the total heat that we gave to ice to make sure it came to the reference point? We gave it Q1 plus Q2, that is 16,500 plus 1000. It's around 17,500 calories, right? If you talk about steam over here, you can say that three heats were added over there. The summation of the three heats came out to be 6,050 calories. There is a deficit between both, right? But what now we have is that at reference point, we have both ice and steam. If we take heat from steam, if we give some heat to ice, everything has come to reference point and we have a total mass of 210 grams, right? And just try to see how much heat you gave and how much heat you took. You gave some 17,500 calories to ice to get it to reference point, while you only took 6,050 from steam. So obviously you've given a lot of extra heat to ice. How much extra? Very easy to say. The difference of these two is the extra heat that has been given to this mixture. That is 11,450 calories. So if this heat we gave in extra to this mixture, that is 210 gram at 0 degrees Celsius water, what we need to do is we need to take this heat out. If we take this heat out, we can get the amount of ice and we can also get the amount of water that is remaining, right? So step 4 was to give or take the heat accordingly to get to the final result. Now, if we take back this 11,450 calorie of heat from the mixture, we can get the amount of ice M that is present in the mixture. So all you need to do is put 11,450 equal to M into L, where M would be the amount of ice that is formed. You'll get this amount quite easily as 143.125 gram. There's a little bit of calculation. I hope that you can do that. And the remaining part, that is 210, that is 210 minus 143.125 would give you the amount of water remaining, that is 66.875 gram, approximately 67 gram. And now you know that everything is going to be present at 0 degrees Celsius. So you have answered both the questions. What is the final temperature of the mixture? You can say that it is 0 degrees Celsius, and you can be double sure because now you can tell the contents of the mixture as well, that how much ice is present and how much water is present. I hope you liked this method. Thanks a lot for watching this. If you have any questions, you can contact me at udit1303@gmail.com. Thanks a lot for watching this video. See you later.